Welcome back to the deep dive. Today, we are tackling a subject that I think every single person listening has experienced at some point. It's that feeling when you're reading a massive 50-page report for work, and you ask a question about a very specific detail buried somewhere in the middle, and you just get, well, a completely blank stare from your own brain.
Right, yeah. It's the classic in one ear, out the other.
Mm.
But we're applying that concept directly to artificial intelligence.
Exactly. We are diving into a brand new paper today. It's titled LongRAG, a dual perspective retrieval augmented generation paradigm for long context question answering, which is, it's a very dense title. Usually when I see a title that long, I assume I'm going to need a second cup of coffee just to get through the abstract.
It is a mouthful, definitely.
But the problem it solves is just incredibly relatable for anyone using AI right now. It's really about why AI gets, for lack of a better term, stupid when you give it too much reading material all at once.
That is a very charitable way of putting it. But yes, technically the researchers are talking about the lost in the middle phenomenon.
Right.
It's a pervasive, well-documented issue where large language models, or LLMs, tend to focus really heavily on the beginning of a document and the end of the document.
Yeah.
But they sort of just gloss over or entirely forget the information that's buried right in the middle.
Which is a huge problem if the actual answer to your question is on, say, page 50 of a 100-page document. The AI essentially skims the intro, skims the conclusion, and just pretends it read the whole text.
Precisely. And the stakes here are actually quite high. We aren't just talking about a basic chatbot that can summarize a short news article for you. We are looking at long context question answering, or LCQA.
Okay, let's break that down for the listener.
Sure. This is the ability to reason over massive amounts of text to answer complex multi-hop questions.
Multi-hop questions. I've seen this term a lot in the research. How's that different from a normal question?
Right, so a simple question is just a direct retrieval. You ask, who is the president? The system scans the text, finds the name, and says the name. Done.
Very straightforward.
Exactly. But a multi-hop question requires multiple steps of logic. So a multi-hop question would be something like, who is the president? And did they attend the same university as the author of the specific book mentioned in paragraph 4?
Oh, wow. Okay, so you have to find the president, then you have to find the book in paragraph 4, identify the author of that book, look up their university, and then finally compare the two universities.
Exactly. You have to connect piece A to piece B to finally arrive at answer C. It requires active reasoning, not just basic text retrieval.
I see. So it's not just looking up a single fact, it's building a complete logical case based on scattered information.
Correct. And the current standard methodology for helping AI do this kind of work is something called LRGAG, or Retrieval-Augmented Generation. But as we're going to explore in this deep dive, standard LRGAG has a fatal flaw when it comes to long, complex texts.
And that is exactly where our main subject for today comes in, LongRAG. It's a new methodology that promises to fix this specific problem by looking at information from a dual perspective.
That's the absolute key phrase here, dual perspective. It balances the big picture, which the authors call global information, with the highly specific facts, which they call factual details.
So it's a whole new way of organizing the data flow.
It's a fascinating structural approach because it forces the AI to process text on two completely different cognitive levels.
So let's really unpack this methodology. Because to thoroughly understand why LongRAG works, we need to completely understand why the current method is failing so badly. We mentioned vanilla ARG earlier.
Right, the baseline standard.
It's the industry standard right now. But let's look at the actual mechanics of why it breaks down. If you feed a massive document into a model with a huge context window, like one of the 128K models, why does it fail? They have the memory capacity, technically.
They do have the capacity, yes. But to understand why it breaks, we have to look at how their attention mechanisms work mathematically. Even though they can technically ingest hundreds of pages at once, they're statistically proven to degrade in performance when the crucial evidence is in the middle of the text array.
So it's not a memory storage issue, it's an attention allocation issue.
Precisely. The architecture of these models prioritizes the immediate prompt at the very end of the input and the primary context at the very beginning. The middle becomes a blur of probabilities. So engineers invented RAG to circumvent this limitation.
And RISE is basically just cutting the long document up into smaller pieces, right? Instead of feeding the whole text, you feed it isolated snippets.
Correct. Vanilla RAG takes a long document and chops it into small, fixed-size bits. They call them chunks. Then when you ask a question, a search algorithm looks for the specific chunks that are mathematically similar to your question, and it feeds only those small bits to the final AI model.
Okay, logically that sounds very efficient. Instead of forcing the AI to read the entire library, you just hand it the 3 or 4 relevant pages. But you're saying this chopping process is actually the core problem.
It is efficient for simple single-hop facts. But for complex narratives, this chopping mechanism creates two major architectural flaws. The first flaw is what the authors call disrupted global information.
Right, I saw a really stark example of this in the paper's methodology section involving the comedian Kathy Griffin. Can we walk through that? Because I think it perfectly illustrates the problem with fixed chunking.
It's a perfect example. So imagine you have a long biographical text about Kathy Griffin, and you ask the AI a multi-hop question. The question is, where did the performer of the song all graduate from?
Simple enough structure. Find who sang the song, then find where that person went to school.
Exactly. Well, the original text clearly states that Kathy Griffin recorded the song. I'll say it. But then, let's say the chunking algorithm cuts the text off right after her name. It just hits its arbitrary word limit. The next chunk picks up with the phrase, study drama at the Lee Strasberg Institute.
I see the problem. One chunk has the song title and the name Griffin. The subsequent chunk has the educational institution. But the semantic connection, the actual grammatical sentence linking them, was completely severed by the chunking algorithm.
Exactly. The global context is broken. The search system retrieves the chunk about the song, so the AI knows Kathy Griffin is the singer. But the system might not retrieve the chunk about the school at all, because that second chunk doesn't mention the song title, nor does it explicitly mention the name Kathy Griffin if the sentence just started with the pronoun she.
So the AI is sitting there with an isolated fragment that says Kathy Griffin sang the song, and it has absolutely no way to connect it to the school because the necessary bridge between those two facts was left out of the retrieved data.
Precisely. And in the paper's actual test of vanilla RAG using this example, the AI completely hallucinated. It found a mention of Seoul Arts College in a totally different, unrelated paragraph that happened to be in the same chunk, and it confidently declared that as the final answer.
Wow. So that's flaw number one. Chopping breaks the narrative context. What is flaw number two in the standard methodology?
Flaw number 2 is defined as low evidence density, which is a technical way of describing a severe noise-to-signal ratio problem.
So finding a specific fact in a massive text block.
Yes. In a long document, the actual required answer might literally be one single sentence. But vanilla RAG retrieves entire chunks. If the source document is enormous, the system ends up retrieving a massive amount of irrelevant text alongside the correct sentence.
So the AI just gets overwhelmed with useless data.
It gets completely confused. When the evidence density is low meaning, there is very little actual signal amidst a massive amount of text noise. The language model often just gives up, or again, it just hallucinates an answer to satisfy the user's prompt.
So to summarize the methodology's primary objective, we need a system that keeps the broad context entirely intact to solve the severed connection problem, but we simultaneously need a system that violently filters out the noise so the AI doesn't get distracted.
Precisely. We fundamentally need global information to understand the structure of the narrative, and we need factual details to precisely prove the final answer.
Which brings us directly to the LongRAG methodology. This paper proposes a dual perspective paradigm. Let's get into the actual mechanics of how they achieve this.
The architecture is very specific. They built a processing pipeline with 4 distinct plug-and-play components. And that term, plug-and-play, is crucial here. It means the methodology isn't tied to one specific language model. You can swap the underlying AI models out depending on your resources.
Okay, let's just list the 4 components clearly before we deep dive into how each one functions.
Absolutely. The 4 steps are the hybrid retriever, the LLM-augmented Information Extractor, the CoT-guided Filter, and finally the LLM-augmented Generator.
Okay, that is a lot of terminology, but based on the source material, the intuition here is quite clear. It's about separating the macro view from the micro view.
Yes, the entire methodology is designed to force the processing pipeline to look at the data in these 2 distinct ways before it ever attempts to generate a final answer to the user's question. It actively synthesizes a broad structural view and a hyper-focused factual view.
Let's start at the very beginning of this pipeline. Step 1 is the hybrid retriever. This is the component that actually scans the database and finds the relevant text in the first place. Now, usually, retrieval is just a basic similarity search. How is this component fundamentally different from the standard chop and search method we just discussed?
Well, first and foremost, they completely change how they chunk the text. Remember how vanilla R just slices the text at arbitrary mathematical word counts? LongRAG employs a sliding window technique.
Explain the mechanics of a sliding window. Why does that specifically fix the severed sentence problem?
Imagine you are processing a long paragraph. In standard LRGAG, you might hard cut the text exactly at word 100. If the subject of a critical sentence is at word 98 and the verb is at word 102, you have permanently severed the semantic meaning of that sentence.
Right. Kathy Griffin is in chunk A, and static drama is in chunk B.
With a sliding window approach, they might cut the first chunk at word 100, but the second chunk doesn't start at word 101. The second chunk actually starts back at word 50.
Oh, I see. So there is a massive intentional overlap between the chunks.
Exactly. There's a 50% overlap, so words 50 through 100 appear in both consecutive chunks. This mechanical overlap ensures that no matter where the cut happens to fall, the semantic connection, the actual grammatical relationship between the subject and the verb, is fully preserved in at least one of those chunks.
That makes perfect sense. It ensures the linguistic bridge is never broken.
Exactly. But the hybrid part of the name refers to the search technology itself. They use a distinct two-stage retrieval process. First, they execute a coarse-grained search using a dual encoder. Then they execute a fine-grained search using a cross-encoder.
Okay, let's pause there. Dual encoder and cross encoder. These are terms that come up constantly in retrieval architecture. But what is the actual functional difference in how they process text? Why does LongRAG explicitly require both?
To understand why the hybrid retriever is necessary, we have to look at the computational reality of similarity matching. In a standard setup, you're almost always using a dual encoder. It independently converts your user question into a mathematical vector, and it independently converts every document chunk into a vector. Then it simply calculates the mathematical distance between those 2 points in space.
So it's essentially just checking coordinates on a massive multidimensional grid.
Exactly. And it is incredibly fast because all the document vectors are pre-calculated and stored in a database. You just look up the coordinates. But dual encoders compress complex semantic meaning. They inherently sacrifice deep linguistic nuance for retrieval speed. They might determine that the word apple as a fruit and Apple as a technology company are mathematically close because the character string is identical, even if the surrounding context is totally different.
So it lacks true comprehension. That's why we need the second stage, the fine-grained search.
Right. This is where the cross-encoder comes in. Unlike the dual encoder, which processes the question and the document completely separately, the cross-encoder processes them together simultaneously as a single unified input pair.
How does that change the outcome?
It allows the model's attention mechanisms to cross-reference every single word in the user query directly against every single word in the document text. It actively analyzes the deep grammatical and semantic interactions between the two texts. It doesn't just check coordinates. It asks, how accurately does this specific passage directly answer the premise of this specific question?
That sounds vastly superior. If the cross-encoder is that much smarter, why bother with the first step at all? Why not just run the cross-encoder on the entire database from the start?
Pure computational cost. A cross-encoder is incredibly resource-heavy. If you ran a full cross-encoder search against a library of 1 million documents, you would literally be waiting days or weeks for a single answer. It requires a massive amount of live processing power for every individual comparison.
Ah, okay. So the LongRAG methodology uses the fast dual encoder as a massive funnel, wide and fast at the top to clear out the obvious junk.
Exactly. It whittles the massive database down to the top, say, 100 most likely candidates. Then, the cross-encoder steps in to rigorously analyze and rank those top 100 candidates to find the absolute top 10 perfect matches. The paper refers to these as PC. This entire hybrid process ensures that before the system even begins the complex reasoning phases, it is starting with the highest possible quality of raw text material.
Okay, so step 1 is complete. We have our highly curated pile of overlapping chunks. Now, in standard vanilla RAG, we would just dump these chunks straight into the final generator and hope for the best. But LongRAG introduces a massive pivot here. Step 2 is the LLM-augmented Information Extractor.
Yes, and this is where the methodology truly innovates. This specific step is designed to fundamentally solve that disrupted global information flow we talked about.
The broken context problem.
Right, because right now we just have these isolated chunks. They are highly relevant snippets, but they're entirely out of order and completely devoid of their original surrounding context. So the information extractor utilizes a very specific mapping strategy.
What exactly are they mapping?
It takes those highly ranked chunks, the PC chunks we just retrieved, And it mechanically maps them back to their original full-length parent paragraphs in the source document. The authors refer to these full paragraphs as P.
Wait, let me stop you right there. We just spent a significant amount of time detailing how chunking the text was absolutely necessary because the AI models cannot effectively process massive blocks of text. Now you're saying that once LongRAG finds a relevant chunk, it intentionally goes back and pulls the entire surrounding paragraph.
It sounds completely counterintuitive at first glance, I agree.
It sounds like we are entirely undoing the retrieval work. If the original document was too dense, aren't we just intentionally flooding the context window again and causing the exact same lost-in-the-middle problem?
That is exactly why the dual perspective architecture is so vital. You are entirely correct. If we just took those massive reassembled paragraphs and fed them directly into the final answer generator, we would immediately degrade the model's performance.
So what is the actual process for handling these massive blocks of text?
They process them entirely separately first. This is the core function of the information extractor. They take that massive expanded paragraph, which could easily be thousands of tokens long, and they feed it into a specialized intermediary LLM with a highly specific singular instruction. Extract the global information. They refer to this output as IG.
Global information. How does the methodology define that? Is it just generating a standard summary?
It's significantly more structured than a basic summary. The model is explicitly trained to temporarily ignore specific granular details like exact dates or minor numerical values, and instead explicitly map the structural relationships within the text.
What kind of relationships?
Relational facts. For example, identifying that person A is the sibling of person B, or establishing that event X was the direct catalyst for event Y. It dynamically compresses a massive winding paragraph into a very dense, highly coherent map of structural facts.
I see. So we are absolutely not feeding the raw, unedited, long paragraph to the final generation stage. We are feeding a highly distilled structural map of that paragraph.
Exactly, and this completely resolves the disrupted global information flaw. By forcing the model to analyze the full, unchunked paragraph in this intermediary step, the extractor model clearly sees that Kathy Griffin is the direct subject of the sentence located 3 lines further down. It explicitly captures that semantic link in its generated summary, the IG, even if the initial retrieval only triggered on the song title. It synthesizes a macro-level view of the entire narrative structure.
Okay, that is a brilliant structural workaround. So now we have the macro view, we have the relationships mapped out, but we still have the second major flaw to deal with, the low evidence density, the noise problem. We have the broad story, but we still have a massive amount of irrelevant text floating around in these expanded paragraphs.
And that leads us directly into step 3 of the methodology, the CoT-guided filter. This component is exclusively responsible for isolating the specific verifiable microfacts.
CO stands for chain of thought, correct?
Yes, chain of thought reasoning. It's a foundational concept in advanced prompt engineering. It's the proven methodology that a language model will perform significantly better on complex tasks if you force it to explicitly generate a step-by-step logical plan before it attempts to generate the final output.
So how does the filtering component actually utilize chain of thought?
We have to look at how standard filters fail first. Standard filtering mechanisms in other Archie architectures generally operate on basic semantic similarity. They look at an individual chunk in total isolation and ask, is this text semantically relevant to the user's prompt?
Which is just a binary yes or no based on keyword proximity.
Exactly. But for complex, multi-hop questions, like say, who died earlier, person A or person B, a single retrieved chunk might appear completely irrelevant if analyzed in pure isolation.
Right. If the system evaluates a chunk that simply says, person A passed away in 1990, and the system asks the standard filter, is this relevant to the question of who died earlier, the filter might actually discard it because that specific chunk contains zero mention of person B or any comparative language.
You've hit the exact failure point. A standard similarity filter completely lacks the overarching logical context to understand that locating person A's date of death is step 1 of a multi-step solution. That is precisely why the chain of thought integration in LongRAG is so critical. LongRAG executes this filtering process in 2 highly distinct stages.
Walk us through those 2 stages. What happens first?
Stage 1 is CoT guidance. The system takes all the retrieved text chunks and processes them together as a unified group. It then instructs an LLM to generate a logical, step-by-step reasoning path that would be required to solve the original user question based on the provided text.
So it defines the operational strategy first. It analyzes the problem and outputs a plan saying, to answer this, I must first locate the death date of person A, then I must locate the death date of person B, and finally, I must chronologically compare those two dates.
Correct. It intentionally does not attempt to formulate the final answer during this stage. It exclusively builds the logical roadmap.
And once it has that roadmap, what is stage 2?
Stage 2 is the actual execution of the filtering. Now, the system iterates back through every single individual chunk of retrieved text. But instead of asking the standard question of broad relevance, it asks a highly targeted question. Does the specific information in this chunk directly support any of the specific logical steps outlined in the chain of thought roadmap we just generated?
Oh, that is a massive operational shift. So it evaluates the chunk containing person A died in 1990, and it cross-references the roadmap and says, yes, this exact data point fulfills step 1 of the logical plan. Therefore, we retain it.
Precisely. It formally assigns a true or false validation label to every single chunk based purely on logical utility, not semantic keyword overlap. The final output of this stage is a highly curated, pristine set of text they call factual details, or ID. This specific output boasts an incredibly high evidence density.
And how does this explicitly compare to other advanced filtering methodologies currently in use? The paper mentions CRAG, for instance.
Corrective RAG, or CRAG, is a very popular advanced framework, but CRAG fundamentally evaluates the utility of retrieved chunks individually in isolation. It entirely misses the logical dependencies between disparate chunks. LongRAG explicitly recognizes and maps those logical dependencies through the chain of thought generation before it ever begins the filtering process. It knows exactly what missing variables it is searching for.
So at this point in the pipeline, we have completely processed the text from two distinct perspectives. We have our macro-level context, the global information extracted from the fully reassembled paragraphs, and we have our micro-level data, the highly specific, filtered factual details that directly populate the variables in our logic chain.
And that brings us to the final operational stage. Step 4, the LLM-augmented generator.
This is where the actual answer is finally synthesized.
Yes. The generator, denoted as G in the methodology, is the final LLM in the pipeline. It takes both distinct outputs as its direct input prompt. It ingests the global context IG and the detailed facts ID alongside the original user question.
So it actively forces the broad narrative structure to interact directly with the verified factual evidence.
The final outcome is the precise answer, denoted as A. Because the input data is incredibly clean, entirely free of noise, thanks to the CoT filter, and structurally coherent, thanks to the paragraph mapping and extraction, the final generation is vastly more accurate and significantly less prone to hallucination than standard RG outputs.
And there is a metric in the paper regarding this final generation stage that I think is incredibly counterintuitive, especially regarding computational efficiency. You would logically assume that running all these extra intermediary LLM processes, the mapping, the expanding, the extracting, the filtering, would result in a massive explosion of token usage.
And it absolutely seems like it would be incredibly computationally expensive.
But if you examine the token flow data, specifically figure 3 in the methodology section, the LongRAG architecture actually feeds significantly fewer total tokens into the final generator model than competing advanced methodologies.
It's a striking data point.
How is that mathematically possible? We explicitly expanded the text chunks back into massive paragraphs during step 2. We literally increased the total volume of text being processed.
We did expand the text volume in the middle of the pipeline, yes. But the CoT-guided filter in step 3 is so aggressive and so logically precise that it systematically discards almost all of the surrounding text noise. The final aggregated packet of information that is actually passed to the final generator model is remarkably tiny, incredibly dense, and contains almost pure signal.
So while the intermediary steps require processing power, the final, most complex generation step is incredibly cheap and fast.
Exactly. It radically reduces latency during final answer generation, and more importantly, it absolutely prevents the final model from suffering from the lost-in-the-middle degradation, because the context window is kept intentionally small and dense.
It's essentially the difference between dumping a 1,000-page legal discovery box on a lawyer's desk and saying, figure it out, versus handing them a 2-page executive summary with 3 highlighted evidentiary exhibits.
And naturally, the system processing the clean, structured summary makes a significantly faster and vastly more accurate final determination.
So we have thoroughly mapped out this entire 4-step architecture. But an architecture is ultimately just an empty operational framework. You need an appropriately trained model to actually execute these commands. And this leads us to a crucial section of the methodology. You cannot just take a standard, off-the-shelf conversational model like a basic Llama 3 or GPT-4 and expect it to inherently understand how to execute a CoT-guided filter command, right?
No, absolutely not. Standard-based models are primarily optimized for conversational dialogue, general text completion, or basic summarization. They are entirely unequipped to natively process these highly rigid, multi-stage architectural commands with the required precision.
So the researchers had to explicitly train the models to function within this pipeline.
They did.
The methodology refers to this as instruction tuning. Walk us through the exact process they used to build the operational intelligence for this framework. This is section 7 in the paper, detailing the learning process.
They had to construct a highly specialized training dataset, which they named LRGinstruction. And the methodology behind constructing this dataset is frankly one of the most fascinating aspects of the paper. They absolutely did not employ human annotators to manually read paragraphs and write out thousands of global summaries and logic chains.
Because that would be incredibly slow and prohibitively expensive.
Exactly. It would take months and cost a fortune. So instead, they fully automated the creation of the training data.
How exactly do you automate the creation of complex reasoning data?
They utilized a teacher-student training paradigm. They deployed a significantly larger, highly advanced LLM. Specifically, they used ChatGLM332B to act as the teacher model. They engineered a fully automated pipeline where this massive teacher model programmatically generated the training examples, which were then used to fine-tune the smaller, specialized student models that would eventually run the LongRAG pipeline.
So a massive AI model is essentially writing the custom textbooks to teach the smaller AI models how to perform these specific architectural tasks.
That's exactly how the pipeline operates. And the methodology explicitly details 4 distinct categories of training data that the teacher model generated.
Let's clearly break down those 4 specific data types. What is the first category?
The first category is extractor data. To generate this, they fed massive Wikipedia paragraphs into the teacher model and strictly prompted it to output structural summaries, focused entirely on global context and entity relationships. They then use these input-output pairs to train the student model. The implicit instruction being, when you ingest a massive block of text, output a relational map exactly like this one.
Okay, so that explicitly trains the model for step 2 of the architecture, the macro-level extraction. What is the second category?
The second category is CoT-guiding data. For this, they provided the teacher model with a complex multi-hop question and the corresponding set of raw text chunks. They then prompted the teacher to generate the explicit, step-by-step logic chain required to solve the problem.
So this trains the model to formulate the operational roadmap before attempting an answer.
Exactly. It teaches the model the fundamental skill of logical planning. The third category is filtering data, and the construction of this data type is highly specific. They provided the teacher model with the logic chain generated in the previous step, alongside one specific individual text chunk. They then forced the teacher model to output a strict binary validation, yes or no, regarding whether that specific chunk contained data fulfilling any step in the logic chain.
So that explicitly trains the strict filtering judgment required for step 3.
Correct. And finally, the fourth category is simply task-oriented data. This is essentially standard question and answer pair data.
Just to ensure the model maintains its baseline ability to comprehend language and generate coherent text.
Exactly. You don't want the model to become so hyper-specialized in filtering that it forgets how to formulate a standard sentence.
Now, regarding this training process, there is a specific metric in the methodology that is honestly staggering. When we usually discuss fine-tuning LLMs, we are talking about processing millions of data points, requiring massive GPU clusters running for days.
Right. Massive computational investment.
But according to the paper, what was the actual volume of training samples they used to achieve state-of-the-art performance with these student models?
The researchers' empirical data shows that fine-tuning the models with a mere 2,600 specialized samples for the extraction and filtering tasks was completely sufficient to achieve optimal performance within the LongRAG architecture.
Only 2,600 samples. That is a remarkably low number. Why is the required data volume so incredibly small for such a complex methodology?
It highlights a critical distinction in machine learning between knowledge injection and behavioral instruction. If you're attempting to teach a base model thousands of new empirical facts, like historical dates or medical terminology, you absolutely require millions of data points. But if you are simply teaching an already capable model a new operational behavior, like how to format a summary or how to execute a binary filter based on provided text, you do not require massive volume. You only require a very small set of exceptionally high-quality, perfectly formatted examples.
So you aren't teaching the model new information. You are strictly teaching it a new set of rules for processing the information it is given.
Exactly. And this specific finding makes LongRAG an incredibly accessible framework. You do not need a massive enterprise budget to fine-tune your own internal models to utilize this pipeline. You just need this highly curated, very small data set.
Okay, so the methodology is computationally efficient. It dramatically reduces hallucination through strict logical filtering, and it solves the lost in the middle context degradation. It sounds functionally perfect. But going through the methodology section, the authors are very transparent about the systemic limitations. What are the core functional assumptions that could cause this pipeline to fail?
The authors explicitly detail two primary assumptions inherent to the methodology. The first major limitation is what they define as one-time retrieval dependency.
Break down how that limits the system.
The entire operational integrity of the pipeline is completely reliant on the very first step, the hybrid retriever, successfully locating the correct source documents during its initial single pass through the database.
Right, because the downstream extractor and filter components can only process the text they are provided.
Exactly. It operates on a strict one-pass assumption. If the initial dual encoder search completely misses the critical document, perhaps because the vocabulary used in the question was entirely different from the vocabulary in the text, the downstream logic components absolutely cannot recover. They cannot filter or extract answers from text that was never retrieved.
So if the initial search fails, the entire complex architecture is effectively useless for that specific query.
Yes. The authors explicitly discuss the necessity of developing adaptive, multi-round retrieval mechanisms as a crucial future improvement. A system where the CoT generation step could theoretically trigger a secondary search if it determines the current chunks are insufficient to complete the logic chain. But currently, LongRAG is a single-shot retrieval system.
And what is the second major limitation detailed in the paper?
The second limitation involves data bias, specifically stemming from the automated teacher-student training paradigm we just discussed.
Right, because the entire LRGinstruction dataset was synthetically generated by ChatGLM3.
Exactly. Because they utilized an automated teacher model to generate the structural summaries and logic chains, there is a significant systemic risk that the smaller student models have directly inherited any inherent reasoning biases, structural flaws, or repetitive phrasing patterns present in that specific teacher model.
The classic garbage in, garbage out paradigm, just applied at a meta-training level. If the teacher model utilizes flawed logic to build a CoT roadmap, the student model is trained to view that flawed logic as the optimal operational standard.
Precisely. It is a known vulnerability when utilizing synthetic data for behavioral alignment.
So having thoroughly examined the underlying architecture, the extraction mapping, the logical filtering, and the training methodology, we need to look at the empirical results. How does this complex pipeline actually perform against current standard methodologies in rigorous benchmarking?
The performance data is highly significant. The researchers benchmarked LongRAG across 3 standard, highly complex, multi-hop QA datasets, specifically Hotpot QA, Music, and 2Wiki multi-hop QA.
And what were the comparative results?
Across those datasets, the LongRAG methodology outperformed standard vanilla R by an average of over 17%.
A 17% absolute gain is massive in current benchmark evaluations. Usually, new architectures yield single-digit marginal improvements.
It is a profound structural validation. Furthermore, it outperformed massive long-context LLMs, the model specifically designed to ingest entire documents without chunking, by roughly 7%. And it also outperformed other advanced multi-stage RAG frameworks like self-RAG by approximately 6%.
But looking at the data tables, the most disruptive finding is regarding model scale, the transferability results.
Yes, the scale comparison is the most compelling argument for the methodology. The empirical data proves that deploying the LongRAG architecture utilizing a very small open-source model, specifically they tested a Llama 2.7b model, routinely outperformed massive, state-of-the-art proprietary models like GPT 3.5 when those larger models were restricted to standard RAG pipelines.
That is a fundamental paradigm shift. The highly compact 7 billion parameter model, something you can run locally with relatively standard hardware, when equipped with this specific dual perspective processing structure, actually yields higher accuracy on complex reasoning tasks than models exponentially larger and exponentially more expensive.
It empirically demonstrates that optimizing the structural flow of information through the pipeline is vastly more critical to final accuracy than simply increasing the raw parameter count of the underlying language model. A highly structured, logically filtered process consistently beats a massive unstructured processing capacity.
That structural efficiency is a fascinating takeaway.
It is.
So, to comprehensively summarize the LongRAG methodology we have analyzed today, the core objective was solving the context degradation of the lost-in-the-middle phenomenon during complex retrieval tasks.
Correct.
Step 1. The pipeline retrieves data using a sliding window chunking mechanism to preserve semantic sentence structures, utilizing a hybrid fast and slow search to ensure maximum initial relevance.
Step 2. The pipeline maps those chunks back to their full source paragraphs and utilizes an LLM to extract a macro-level map of relational facts, entirely fixing the broken context flaw.
Step 3. The pipeline generates a step-by-step logic chain based on the query and rigorously filters the granular details by validating each chunk against that specific logical roadmap, thereby completely eliminating text noise.
And finally, step 4. The pipeline synthesizes the final answer by directly prompting the generator model with both the extracted macro structure and the verified microfacts.
It fundamentally solves the attention degradation problem not by blindly attempting to expand the model's memory capacity, but by systematically pre-structuring and pre-filtering the text before the final model ever engages with it.
Exactly. It forces the system to respect the macro complexity of long narrative structures, while simultaneously demanding the absolute precision of isolated factual data.
As we wrap up this deep dive, I want to leave everyone with a broader architectural thought based on that final benchmark result. We are currently watching massive tech companies engage in an absolute arms race to build language models with ever-expanding context windows. They are pushing models that can ingest millions of tokens simultaneously, under the assumption that simply feeding the model the entire database will inherently solve complex reasoning problems.
Which the data clearly indicates is an inefficient approach. The biological and mechanical limits of attention mechanisms mean that simply increasing the volume of input data simultaneously increases the density of the noise, inevitably leading to reasoning degradation.
Exactly, and the LongRAG methodology proves that a vastly smaller model, utilizing a highly regimented, multi-stage filtering architecture, can consistently outperform those massive context windows.
It suggests the future of complex AI architecture isn't merely building larger monolithic models, but rather designing compound AI systems. Systems that compartmentalize retrieval, structural extraction, logical filtering, and final generation into entirely separate, highly optimized operational steps.
So the ultimate question for anyone currently engineering enterprise AI pipelines is this: are you simply paying to access a larger, more expensive brain? Or are you investing in building a fundamentally superior filing system? Because based on the LongRAG data, the superior filing system is winning the race.
That is precisely the architectural debate this paper initiates.
Well, thank you so much for breaking down the technical mechanics of this methodology with us. It's been an incredibly informative deep dive.
Absolutely, it was a pleasure.
And to our listeners, thank you for joining us. Keep analyzing those architectures, and we will catch you on the next deep dive.